I welcome you all to the week 10 for the problem solving session for the course Ultrafast Laser Spectroscopy. As the previous weeks, this week also we'll be discussing the assignment questions and maybe the new problems which are related to the concepts which have been discussed in this session. Okay, at present, I can see no one is there, so we'll wait for some time and then we'll continue with the problem solving. Yeah, okay. So it's time now. So it's better we start the session. First of all, I'll be sharing my screen. So, as you all know, this is the session 10 for the course Ultrafast Laser Spectroscopy, which is guided by the instructor, Professor Anindya Datta sir, and I'm Nikita Mahajan, who is the teaching assistant for this course. So, continuing with this, we'll be discussing the various problems which were discussed in the week 10, or there are various questions which were given in the assignment, and I'll be helping you out with whatever doubts you have in those questions. So, starting with this, the first question given to us was the question one reads as 7 ESA indole dimers are good model of. Okay. So, first of all, let us know what is the 7 ESA indole dimer, and then we'll come to a conclusion how it is similar to what. So, first of all, we'll draw the 7 ESA indole dimer. So, as the name suggests, it has an indole ring and also a nitrogen. Say, this is the structure where you have a six-membered PDD ring like this, and there is one more indole ring connected to it. As you know, in indole there is a proton this side, and there also we can say that the lone pair of this in nitrogen of this indole ring is delocalized within the ring, and the lone pair of this nitrogen is somewhere outside of this aromatic 6 pi electron ring system. And if you take the talk about the dimers, it is so see the in this case the nitrogen, this nitrogen, it is sp2 hybridized, while in this case this is sp3 hybridized. So first we'll draw one more azindole derivative which is just opposite, so that we can just show the representation of how the dimer looks like. Okay, so somewhere here the nitrogen is with a lone pair. Okay, and if you talk about the pi bonds, they are like this. Now, what happens is we have studied a process called the photoacidity. Okay, photoacidity and photobasicity. So what does this photoacidity and basicity mean? This means that when you irradiate any photoacid or a photobase with the light, then what happens? It becomes more acidic than it was previously. For example, if you talk about say beta naphthol, the pKa or say the acidity of beta naphthol is less when it is not irradiated with light. Simultaneously, if it is irradiated with light of a particular frequency, then you will see that the pKa will reduce to 2 in the presence of light, and the pKa normally is say 9.2. So this is the case. Now why I have brought this term here? So these 7 as a 7 as a indole, normally in normal situations they do not form the dimers. They as you can say, they form the dimers only at higher concentration. Okay. And when this concentration is reached that high that they can form dimers, they interact in a way that this hydrogen, or if it is not visible, say this hydrogen or this proton is hydrogen bonded with the nitrogen of the other azindol molecule, the sp2 hybridized nitrogen. And in this case, this similarly the vice versa, this is to the other molecules, and in this way the two interact. Okay, now this model, they have told like how they it is related to. Suppose you talk about the amino acids, so amino acids have a CONH bond. Okay, now the cholesterol in the lipid membranes or the histone in the nucleosome. Basically, what here we can see is there is one N which is bonded to H, and therefore the second N which is here, this is sp3 hybridized, and in this case it is the sp2 hybridized one. Due to the difference in electronegativity, this hydrogen becomes hydrogen bonded to this pyridine sort of nitrogen which has a lone pair that is outside. Okay, now if here I have kept structure which I have taken from internet only. See, there are, these are the new say these are the nitrogenous bases. Okay, what are these? This is adenine, and this is adenine, and this is thymine. Now if we all are well aware of these type of nitrogenous bases that are present in the DNA. Okay, so there are four bases. Those are adenine, I represented by A. Second is thymine. The third one is guanosine, guanine, or and the fourth one is cytosine. So these four are present in the DNA, and here the structure is somewhat which is is exactly what is represented in this figure. That is, this is adenine and thymine. And if you talk about the double helical structure which was given by Watson and Crick, you could get that double helix, the only reason for it to be in the form of double helix was that there was these base pairs, they had formed the hydrogen bonds. Now talking about A and T, these are the A, it forms two hydrogen bonds with the thymine, and the G, it forms, or say guanine forms three hydrogen bond with cytosine. Okay, and if you look carefully here, see this nitrogen and this nitrogen, so it is somewhat similar to what we have seen in the 7-azindol dimers, and therefore in C similarly, and in G and C also you will observe the same thing. So therefore we can say that such type of hydrogen bonding, which is quite more in case of the DNA base stacking, that is similar to what you have observed in 7-indole dimers. Okay, and maybe the molecules are different, but the sort of NH interaction which is observed in both is similar. Okay, so basically, we come to our answer, and that is DNA base pair. And for the for studying the pi stacking in these molecules, many of those have also used the aza-indole dimers as a model to study the DNA base stacking. Okay, so our question was 7 aza-indole dimers are a good model for, and we came to an answer using a structure that is of the base pairs in the DNA, that are the thymine, adenine, thymine, guanine, and cytosine. And when you just carefully compare them, this sort of NH hydrogen bonding is similar to that we have observed in the 7-aza-indole. Now, there was one more topic which I just could not explain in detail, and that was along with this, what how does this or say this type of interaction occur. So on increasing the concentration, these molecules, they assemble each other in a way that the proton that is on the indole ring is transferred or is shared or is hydrogen bonded with that of the pyridine, or say the other molecule, other nitrogen atom, and similarly the vice versa. Okay, So this is the whole answer to this question. If you have any doubt, then we can discuss, or else we can go to the next question. Okay, so we'll go to the next question. In the question second, in the femtosecond fluorescence traces of 7-aza-indole dimers, there is fast decay. Now, in this question, first of all, 7-aza-indole dimers they are talking about, and second thing they have asked in the femtosecond fluorescence traces. Okay, so normally for any dimer which is fluorescence, what we observe, what we know, what we carefully look at is the absorption spectra and the emission spectra. Okay, but what we can say is in both of these cases, the time resolution is quite less. Therefore, the total emission if you get is, say, it is a peak like this. Okay, now what we talked about emission, say in this broadband, there is some emission that happens to be like this, and the other emission after the decay of this step happens to be like this. Okay. Now, since the time resolution is less, you see both of these together in the form of a single peak. Okay. And this is what has happened in the case of 7-aza-indole dimers. Now, why is the need of this femtosecond fluorescence? Why? Because according to the studies, it was found that there are existing precursor steps that are also a part of this fluorescence decay. Okay, so for the detailed discussion, I have kept this plot. So when you see that this is sort of the 7-aza-indole derivative or dimer. Okay, when this 7-aza-indole dimer is irradiated with light. Okay, and that too, when you irradiate it with light, then you will see that there is exchange of proton, and not on only a single proton. You see there are two protons, and only one proton is not exchanged to the other. This proton, this is the first proton that goes to this molecule, while the second, say this proton is labeled at 2, it goes to the first one. Okay, now, what was the need of femtosecond resolution? That was similar. That the reason to that was, see here. Say this emission involves two transitions, but both of these are quite fast, and therefore, in the emission you see as a single band, and you do not find them to be separated. And in order to have a detailed study and the study of each transition that occurs, we'll need something that is femtosecond resolution, femtosecond time resolution, so that we can minutely observe with in the range of femtoseconds what are the ultrafast processes going on. So here what they had noticed that like there was a femtosecond time resolved fluorescence experiment conducted, that too at diff and that too at different time intervals. Okay, so the first one is at 320 nanometer, then 350 nanometer, 380 nanometer, 420, and so on. Basically, the first one which they noticed was at 320 nanometer. Okay. The second one is at 350 nanometer. Now, what is this? This is, say, this is the excitation wavelength, which is they have taken as 270 nanometer. Now, see, if you use a very high energy excitation wavelength, then there will be many emissions that can occur. For example, if you have, say, this is the S0 state and this is the S1 state, and these are the upper vibrational levels, and this is the S2 state. So, in this 270 nanometer, say the molecule is exciting to S1 also, and it is exciting to the S2 also. Okay, because the energy which you have provided is quite high. What is the point to notice is, for each nanometer, say for each wavelength of emission, they have recorded a time resolved decay spectra, or where the how the fluorescence intensity is dropping or is decreasing with respect to time. And what is the unit of this time? This time is in the unit of, say, picoseconds. Okay. Now you will observe that, see here, initially at the 320 nanometer, there is a rise, very short rise with a decay. When you record the emission or spectrum at 350 nanometer, then you will see there is quite high intense signal, while and there is a decay, which states that at 350 nanometer there is some emission occurring, which has some decay of this range. Then again at 380 nanometer, this signal is at the decay. Now, what you have observed is, the next is, say, this one, 420, 445 and 455. After 380, when you increase or when you record the spectra at uh, say 420, 445 and 455 nanometer, you see that the intensity of this signal is reducing further. And when this signal is reducing at 455 nanometer, you see there is a slight increase or slight hump, you will notice, very minute hump. Further, on recording the emission spectra at 500, 560 and 620, you will see there is a new signal emerging. Okay, this is the new line. Now, what you want to what is the total conclusion of this observation is, as this signal, this first signal starts to decay and it just diminishes, there is a new signal arising. Okay, and this signal is at higher wavelength, or say longer wavelength. So basically, with the 270 nanometer excitation, you see something at 320, 350, 380 and furthermore, that is a decay signal. That is, which states that some state which had emission in this range, that is decaying. Okay. When you record it at 500 to 560, you will see there is rise in signal. What does this state? This states that there are two signals, right? And what you observe from the emission spectra, that was, or the steady state emission spectra, was only single signal, and here you get the information, know that there are two signals. When the one decays, the other one rises. So now we'll look to what is discussed in the question. In the femtosecond fluorescence traces of 7-aza-indole dimers, first of all, there is fast decay at longer emission. So what we saw at longer emission wavelength was not a fast decay but a rise. So first option is not correct. Then second is, there is rise at the longer emission wavelength. Yeah. So this is the thing that we have observed. When you go to a longer emission wavelength, then you will see there is rise in a signal, unlike the decay which you observed. So this is right option. Then third also we have to consider, because this is an MSQ. Then the third option is this fast component of the decay signal, single exponential, and the second is the fast component of decay is double exponential. Okay. So, do you have any answer to this question? Okay, so this thing we'll be studying later, but so far till now we can just say that this double exponent, this longer wavelength signal is double exponential and not single exponential. Okay. So the fast component of the decay is double exponential and not single exponential. We'll discuss in detail what are the two factors that are affecting. And by this, we come to the right answer for the question number 2. The first is, what is the need for the femtosecond fluorescence? I had discussed, where we discussed that in the absorption and norm emission, that is of the steady state, when you observe, you will observe a single peak. But when you observe the same fluorescence signal at a shorter time or at a higher time resolution, you will notice that there is not even a single peak. It is a mixture of two peaks which have come together, and due to lack of the time resolution, proper time resolution, we cannot see them. Okay. Then when you notice it, or when you observe or give a close observation to the same on the femtosecond time scale, you will notice that in the femtosecond time scale, a signal that is recorded at different wavelength or a different emission wavelength with the excitation of 270 nanometer, you will notice there is a signal from that is at 320 to 380 nanometer. Okay. So that is particularly at 380 nanometer or 320 nanometer observed, while the second one is at 620 nanometer. And in the emission spectra, wait a second. And in the emission spectra, you will see something like this. Okay. The first peak is at, say, 380 nanometer, and the second peak is at, say, between 420 to, or no, 455 to 620 nanometer. Okay. So it starts from 2, say it ends somewhere, but this is at 380 nanometer. Okay. So we'll get two signals, and that too, when you will get these two signals you will get when you have, say, the dimeric state of 7-azindole. Okay. If you have any doubt in this question, you can ask, or else we'll proceed to the next question. Okay. Now we'll go to the next question. That is question number 3. So question number 3, what is it as? The question number 3 is, fluorescence of 7-aza-indole dimers reveals the existence of ultrafast, fast, and third slow components. Contribution to the absorption spectra is made by. Okay. For this, I have given a figure that contains absorption and steady state fluorescence spectra of 7-aza-indole, and how they have noted, or how they have observed the each fluorescence spectra of each component by keeping the time scale to be quite short, and then what are the three components that they have discussed. Okay. And through this we'll come up with the answer. First, this side you will see, this is the molar extinction coefficient, mole inverse, centimeter inverse. This side of the is fluorescence intensity, and on the x-axis is the wavelength in nanometer. Now, when you talk about the absorption, here they have given clearly that is the monomer and dimer. For the monomer and dimer, the absorption for dimer is little bit decreasing in intensity, but there is not very much significant change in the absorption compared to monomer and dimer. Only there is a slight, very slight redshift observed. Now, in the other case, in the similar case, when you observe the spectra or the fluorescence, okay, here what they have told, they have given the each concentration on which they have taken the spectra. So the first one is the pink one, that is the 10 to the power 2, or say we start with 10 to the power minus 4 because this is the lowest concentration. So basically at lowest concentration, the blue line you will see there is no emission in the range of 400 to 600, but there is emission in the range of 300 to 400. Okay, so this you will observe in each and every case, whether the concentration is whatever, but you will observe this fundamental band of fluorescence. Okay, the second one is 10 to the power minus 3. It also gives the similar peak from 300 to 800, but there is one new peak arising that is between say around 420 to 600. Okay, and this data is consistent with the earlier femtosecond resolved time data. Also, in this case, the excitation is at 270 nanometer, as is done always. And the solvent that is taken is n-hexane. In the third case of higher concentration, the pink line you will note, initially the absorbance is similar. And second thing, in this case, there is a new peak that is fully or high intense peak. So in this case, we can say that there is a tautomer formed. What is this tautomer for? This tautomer is the derivative for the double proton exchange that has happened to be in the 7-aza which I had drawn similar like this. Say this is a 6-membered and a 5-membered ring, and it has one proton this side. Similarly, if you talk about dimer, there would be another molecule like this, which is represented is as in this is oriented in this direction, and then you will see that this proton interacts with this, and similarly this proton interacts with this. On giving an excitation of 270 nanometer, you will see this will totally get out from here, from the from the this indolic nitrogen, and it will go to this, the other pyridine. Okay. So then what will happen? Say it has read from this. Okay, it is not this. It is not 6-membered, it is 5-membered. And it has lost the proton and it has gained a proton. And for the other molecule which is in front of it, similarly, it has NH. Okay, I'll just rub it and make it more clear. Okay, so from here only we'll understand what is happening. Say this had a proton. Yeah. So the proton which was supposed to be here, it has come to this and it has come to this. Okay. This has happened on photoexcitation, and this is the tautomer they are talking about. Now this is for the steady state fluorescence spectra. what happens when they take the fluorescence spectrum of each component, and that too at the shorter time scale. So they notice that with the 270 nanometer excitation, you will get the four, say this one is for the monomer, and the there is a second one that is a precursor one that has a very short lifetime of 0.2 picoseconds, which then forms precursor 2, which has comparatively a longer time of 1.1 picoseconds. And as you can see, as this decays, it gives rise to a new tautomer that is that has 3.2 nanoseconds of time range. And from picosecond to nanoseconds, if you can convert, you will notice that it is 10 to the power it is 10 to the power 3, or almost 3000 times more. Okay, so uh, from this spectrum, for each component, your problem or the question which or the observation which was observed in this case has become more clear, that normally what you observe is simply this peak with this peak, right? And that too, at this moment when you get a peak of this, the intensity turns to be zero at some time, then it rises to a maximum for the tautomer. But in the other two cases, for the other two cases, you will see this monomer. Apart from this, there are two precursors in this stage. And how did we get the fluorescence or the detection of these? By a higher time, or sorry, resolution, or say by the time resolution in the level of femtoseconds and picoseconds. You will notice that there is one more precursor which has a lifetime of only 0.2 picoseconds, and the precursor 2, which has comparatively more lifetime, only on a small scale, that is of 1.1 picoseconds. Further, this you can say, which is a dark red line, as it extincts or as it decays, there is a rise of a new signal, which is also consistent with the observation that we had observed in the steady state fluorescence spectra. When they compare the fluorescence of each of this component, they show that there are, first is the ultrafast component, that is the dimeric state, or that has two states. First is the ultrafast state, which has 0.2 picoseconds of fluorescence lifetime and a radiative lifetime of 13 nanoseconds. Okay, but in this whole radiative lifetime, there is a radiative as well as a non-radiative process involved, which is and because of this faster non-radiative decay, you observe that the fluorescence lifetime has decreased to picoseconds range. The second is a fast, although yeah, it is fast. It has peak wavelength at 350 nanometer. Now, if you observe closely this and this line, if you draw a straight line from that, you will notice this is the second one is at a higher wavelength, and that they have told us this is the dimeric S1 state and a tautomer. Now, if you want to draw a simple representation of each of this level, you can say that for each of these state, each of this dimeric state, this is the S1 state, this is the S2 state, and this is the S0 state. Okay, from here what happens? By absorption of energy, the molecule reaches to S0, S1 and S2 both states. As you can see, the intensity of S0 and S, yeah, right. So it reaches to S0, from S0 it reaches to S1 and S2 both the states. Okay, then what happens? This S2, by radiative and non-radiative process, it decays to S1, and then simultaneously this S1, the whole population of S1, it comes down to S0 by emission of radiation, that is of frequency h nu. If you closely see what is the emission of both, say from S2 to S1, it will be at shorter wavelength, since the energy, sorry, at longer wavelength since the energy, and from S1 to S0 it is at this point. Basically, for the monomer stage, if it reaches from the S to S1 to S0, it has a higher energy and therefore lies at a lower wavelength of emission. While in the case of S1 to S0, it is has low energy band gap and therefore it is observed as at a higher wavelength. Okay. From this whole analysis, you observe three states. There is one ultra fast dimeric state, then there is a fast dimeric S1 state, and then there is a slow tautomer state. For the tautomer case, you can see there is it has a lifetime that is 3000 times more than the fast process. And for each of these, the total radiative time is 13, 38, and 160 nanoseconds. For each one, the fluorescence quantum yield is of the order 1.5 into 10 to the power minus 5 and 2.9 into 10 to the power minus 5. What is the slowest one is 2.0 into 10 to the power minus 2. Okay, yeah, so this is the quantum yield that is the highest amongst the two. And what is this oscillator strength? This oscillator strength also denotes the absorbance or the epsilon, and which when you sum up these two values, you will get the epsilon value to be 0.16, which is what you have observed from the absorption spectra. Okay. So basically, the absorption band has both the transitions that are covered. Okay. So in this absorption, both the bands which you have observed separately, their absorption occurs same way, similar in this at the same range. And but this absorption involves the transition from two states. Okay. Now, what our question was? Then uh, the fluorescence of 7-aza indole reveals the existence of these diseases. Contribution to the absorption spectrum is made by. So here what you have noticed that the oscillator strength when we calculate for the individual components. This is the oscillator strength which we got from the absorption. When you compare the two, what you get is 0.16 from the absorption, which is the sum of these two individual components. Through this experimental data, we can conclude that the absorption band includes both transitions. Okay. And for these transitions, what are these transitions? The first one is the ultra fast one, the second one is the fast one. What are these? Yeah. The first one is the ultra fast one, the second one is the fast. So, the absorption is made up of these two ultra fast and fast processes that are the part of it. So for this, first and stood for ultra fast, second for fast, and the third for slow components. So basically, the slow component does not contribute to absorption. The absorption is only for these two processes. So answer for our question would be first and second, not second and third, third and first, second, third. Okay. If you got the answer right and there is no problem, then we can proceed, or else I'll wait for some time so that you can bring your doubts up. So we'll go on to the next question, which is question 4 reads as the fluorescence depolarization of 7-aza-indole with time constant of 12 picoseconds is ascribed to. Okay. Now, basically, what is this fluorescence depolarization? So, See, here, this is a diagram that has illustration of each and everything. So, as you have noticed, or say, as we have discussed in the earlier question, if you excite at the 270 nanometer and observe at different time scale with the delay time, actually just for the information, what they have used here is the pump probe experiment, which we had discussed, which I have discussed in the last week module also. Here, what is the delay they have taken, and with the delay time exceeding, how much is the anisotropy or the fluorescence anisotropy happening? What is this fluorescence anisotropy? Fluorescence anisotropy states that the light which is emitted is the sum of the perpendicular and the parallel, or say both the polarized light, say horizontal or vertical. Okay. Now here there is something which should be included. Say that after what has happened is, say, yeah, the molecule has this whole process of the 7-aza-indole circles around that. It is a process in which first initially, after excitation, say from S0, the excitation happens to be in S2 and S1 state, and each this S2 and S1 together form an ensemble. Okay. So, but the system which is at S2 state, by absorbing certain amount of frequency of light, it reaches to the S2 S1 this state. From there, immediately from S2 to S1, there is a relaxation that happens, which is of the time scale of 0.2 picoseconds, say. And after this, there is a double, soon after this step, this is the precursor to step, say, which we discussed in the previous question. From this, immediately a double proton transfer concerted step occurs, where each of the proton or these double protons are being transferred to each species. And from this precursor 2 to the tautomer, the time scale is of 1.1 picoseconds. After this time, this particular molecule, it has a lifetime of 12 picoseconds. Okay. So, the fluorescence depolarization with a time scale of this 12 picosecond mainly ascribes to this the rotation of molecule. Okay. Now the polarization has happened. Sorry, the transfer has happened. This is not a case of twisted intermolecular charge transfer. And in this case, this option is also wrong, because the crossover from the locally excited state to another state without proton transfer. So basically in this step, the proton transfer has already happened. So yeah, this is also not the right option, and the excited state proton transfer is also not happening in this state. So the answer to this fluorescence depolarization of 7-aza-indole with the time constant 12 is 12 picosecond, is the due to this orientational diffusion, or say the rotation of the molecule. Okay. Now, excitation wavelength dependence of the fluorescence. See, in this figure or in this spectra, the anisotropy, say, is somewhat happening in this case. Also, at the time scale of 0.2 picoseconds, you will notice this case, which is not observed in that one of 313. At 313 nanometer excitation, you will get the points are more or less on the same line with the delay time they have observed, which states that you observe only one, say, the fluorescence wavelength at 380 nanometer. So it is involved, or it comprises of only one component, while in this case there are two components also. When you talk about a 270 nanometer, which states that at 270 nanometer, both the excitation from S0 to S1 and S0 to S2 has happened. And meanwhile, if you excite at 330 nanometer from S0, directly the excitation occurs to this S2 state, or say the S1 state, from where you will notice the simple fluorescence decay to S0 only. Okay. So, answer to this question was when the step you observed at the 12 picosecond of which has a lifetime of 12 picosecond is due to the rotation of the molecule and not due to crossover or excited state proton transfer. Okay, if you have any doubt in this question, just ask, or else we'll proceed to the next question. So now the next question, which is also similar to the first question, the fluorescence depolarization of the time constant 7 of 7 as a indole with a time constant of 0.2 picoseconds is ascribed to. Okay, so see this carefully, this graph. This whole decay or this has a time of 0.2 picoseconds. Okay. Now, why is this the depolarization or the fluorescence depolarization? What is the reason for this kind of decay? That is, say, as I told in this whole picture of 7 as a indole, which is somewhere simpler, is a different case from the earlier cases where there is no third state involved. There are two states, S1 and S2. Other than this S1 and S2, there is one more term that is given to this, that is the dimeric S2 and dimeric S1 state. Okay. So, what they have said is by excitation with a longer wavelength, both of the transition will occur. That light will, the system will reach to this S1 state also and S2 state also. Simultaneously, with the function of time from S2, the molecule will relax to the S1 state. And with this thing happening, there will be this whole process will be in a very short time of say 0.2 picoseconds. Okay. And if you just see this diagram, it will be more clear. So basically from S0 to S2, the and S1, the excitation has happened. From S2, immediately by the thermal relaxation, the system has reached from S2 to S1 and within a time of 0.2 picoseconds. From this stage, immediately the system also starts to uh, undergo a double proton transfer, and the reason for this proton transfer is the photobasicity, because we can say that at the higher or say at the on irradiation of these photobases with light, you will notice that the basicity of the particular unit increases to some fold. Because of the basicity increase in this nitrogen atoms, immediately this proton is taken up by it, and thus you will see a double proton transfer happening, which is from the which is for the time 1.1 picosecond. And from this diagram, see here, this precursor, it happens from the ground state, it reaches to this precursor one stage, from where from S2 to S1 relaxation forms a precursor 2. Till now, from precursor 1 to 2, there is no proton transfer happening. As soon as the proton transfer happens, there is shift in the emission of the total. Okay. And thus, the answer to this question was crossover from the locally excited state to another state without proton transfer. So, this 0.2 picoseconds correspond to the thermal relaxation from S2 to S1, which is a non-radiative step. So, what is this? This is a non-radiative step which involves the uh, from the transfer from one state to another state, and is the cause of the fluorescence depolarization. Okay. So in all, so far we have discussed about 7-aza-indole. How does the absorption curve varies with concentration? Okay, sorry, absorption and even emission varies more prominently. Then we have discussed how in the fluorescence spectrum, each of these components which we could not see in the emission spectrum of the steady state fluorescence spectra, we could see on a shorter time scale, where we could notice that there are three fluorescent components. One of them is of the time scale 0.2 femtoseconds, the other one is of 1.1, and the tautomer is of 3.2 nanoseconds. One more point to note is, see, according to the Kasha's rule, we had known that the emission occurs from the lowest excited singlet state. Emission occurs from lowest excited singlet state. So this was Kasha's rule. But this whole process, or the femtosecond resolution, just denies that fact that from S2 to S1, you will, the transition for this particular transition, you will not observe the fluorescence. The fact is, the fluorescence lifetime for this transition is very less, and therefore it is left unnoticed because of this steady state spectra of the other unit. Okay. So the fluorescence lifetime of this is short, because of which it hides somewhere in the original one. Okay. Now we'll go on to the whatever questions we have discussed in short. The first one was 7-aza-indole dimers are similar to what? So we have drawn this structure number of times throughout this discussion. So this is basically the structure, and when you closely observe the structure, it is similar to the DNA base pairing, or say the hydrogen bonding in each of these. Okay, and the fact to notice, in DNA, this A and T, they are bonded to each other through hydrogen bonding, that is two hydrogen bonds, while in case of G and C, guanine and cytosine, there are three hydrogen bonds. Okay, and also uh, the base pairing, you have noticed this NHN, this type of hydrogen is bonding is observed, which is similar to the 7-aza-indole case. In the question second, we had discussed how the femtosecond fluorescence traces can help in a detailed study of the steady state fluorescence spectra which we got. So first of all, the femtosecond fluorescence spectra, what we got, I have just pasted it here for so that we can have a better look on this. And we notice that on the excitation to be constant at 270 nanometer, in each case what you notice is, after changing the emission recording at different wavelengths, at higher wavelengths, you see a hump or a rise in a signal. This rise in signal belongs to, or this longer emission wavelength has rise. And second thing, the fast component is the, because is also a double exponential or bi-exponential function. Why is this by exponential? Because there are two factors that are governing that. Then also we studied there are three components in the fluorescence spectra, that is ultra fast, fast and slow components. And the ultra fast and slow components, how do they vary, and how, what is their fluorescence spectrum for each, we had noticed. And when there was a total study, and the oscillator strength of each was calculated, it was found that the total absorption which is noticed in this dimeric state, it is the contribution to these two, ultra fast and fast. Okay, so the oscillator strength, which is also related to the absorbance, is the sum of these two, which states that the absorption is occurring due to the transition to these two states, the S2 and S1 and S2. Then we also studied the fluorescence depolarization in 7-aza-indole with 12 picoseconds time corresponds to the rotation of the molecule, and the second one we studied how with the change in the excitation wavelength you will get the dependence of the excitation on the fluorescence and isotropy. How is that this working? Then with the time scale of very then the fluorescence depolarization, if the time constant is of 0.2 seconds, which stage or which type of step it includes? So that involves a crossover from the locally excited state to another state, that too without proton transfer. The point to know it is, in this case, in whole picture, the proton transfer is taken to be as a concerted mechanism. Okay, concerted mechanism. That is, the proton transfer occurs in single step, two protons are being transferred. Now we'll go on to the next question. Question number 6. Excitation of 7AI. So AI stands for azindole in the red edge of the absorption spectrum yields a double exponential fluorescence decay intensity but a single exponential anisotropy, a single exponential decay for the fluorescence intensity but a double exponential decay for anisotropy, a double exponential decay for fluorescence intensity as well as anisotropy, a single exponential decay for the fluorescence intensity as well as anisotropy. So here this is for the consideration of fluorescence anisotropy, and you will notice that this is a single exponential decay, not a double exponential decay. Similarly, the decay for both the cases is considered to be single exponential and not a double exponential decay for fluorescence as well as anisotropy. Okay, so the absorption which they have taken at 270 nanometer, see here it will be clear from this diagram, yeah, which is taken as 270 nanometer. The emission for both it is single exponential decay. Okay. If you have any doubt in any of these questions, ask, or else we'll go to the next question. So, our next question is, Kasha's rule is obeyed in most fluorophores because the S2 state is. Okay. Now, we'll discuss a little bit in detail about this thing. So, first thing is, what is the Kasha's rule? So, Kasha's rule states that the emission in any fluorophore occurs from the lowest energy excited state, right? Now, this lowest energy, what is it? In terms of S0, S1 and S2 you talk about, say this one is the S2 state. Okay, earlier whatever we had studied that from S1 to S0, what happens is the radiative emission that we have studied normally. Now, we can also draw an explanation to how the S2 state can be emissive as well. First of all, from the ground state, by absorption of certain higher energy, it reaches to both the states, or the system reaches to both the states S1 and S2. Okay, this happens to be at the same time. As soon as you excite the whole system, then it will reach to S0, S1 as well as S2 state. What happens? There is one more thing to notice. Normally in molecules, okay, so I'll write on the top. Normally, in molecules, the yeah energy gap between S0 to S1 is more than S1 to S2. S1 and S2 lie close to each other. Got it? Now, see, S1 and S2 lie close to each other. Thus, if you excite S1, there is a chance S2, the molecules, some molecules or some part of it, the system will also be excited to S2 state. Okay. Now, see, earlier we noticed that from S2 to S1, what happens? Thermal relaxation. That is the non-radiative process has been happening. Okay. Now, along with this, there is a chance that this S2 to S1 is also an emissive state. Okay, this is emission. But as you can say, the total emission, the total constant or radiative time constant for this is say x, which is the sum of, in the term of picoseconds, which is the sum of kr plus knr. Okay, if the value of nr is quite high, then in this case you will get a very small value for x. Thus, s is the radiative time. Okay, now if value of kr, that is knr, non-radiative, is high, the total radiative time will reduce. Suppose I have taken this to be 10 and this to be also 10. But if you add these two, then it comes to be 1 upon 20 and the answer comes to be 0.05. Right? Now, if the if we calculate fluorescence lifetime, it is 1 upon kr, and because of this 1 upon kr, when you do, the more is the value of kr, the less is the tau of fluorescence, the lifetime of fluorescence. So here comes the answer to our question. The question they had asked is, Kasha's rule is usually obeyed in most fluorophores because the S2 state is. Now what happens in most of the cases is, this from S2 to S1, which has both the steps, the radiative and non-radiative emission. In that case, the the non-radiative emission constant, its value is quite high. Because of this, the whole radiative lifetime reduces. And in this relatively less radiative lifetime, the lifetime of fluorescence is further reduced. So we can say that the S2 state is emissive with a shorter lifetime, which makes it undetected or unresolved. What are the options they have given here? The first option is absolutely non-emissive, is or is completely non-emissive, then is not usually populated by direct electron excitation, is very short-lived and so its emission makes the minuscule contribution to steady state intensity, and is usually undergoes inter-system crossing. Basically, here we have eliminated the point of inter-system crossing, which we are just talking about the internal conversion thing. The second is completely non-emissive. So far from our discussion, we are so sure that this is not totally non-emissive state. The second option is not usually populated by direct electronic excitation. So what we want to say is direct electron excitation can excite both S1 and S2, but from S2 to S1 immediately through a non-radiative decay, the population increases in S1. That is, totally the population gets transferred to S1 state. Also, the third option is usually undergoes intersystem crossing. So these two are also wrong options. The right option is very short lived, and so its emission makes minuscule contribution to steady state intensity. Now see, if you are recording at 0.1 per second, your integration time is so. Can you observe anything that is of the time or scale of picosecond, that is of 10 to the power minus 12 seconds? No, it is practically not possible. I mean, you can observe, but that is somewhere hidden in your total steady state spectrum. Okay, so the answer to this question is short lived, and so its emission makes the minuscule contribution to the steady state intensity. Okay, so now if you have any doubt in this Kasha's rule, and however we came how did we come to the conclusion, feel you can ask. Okay, yeah. So let's take a quick revision of what we had studied. The Kasha's rule states that the emission of the fluorophore occurs at the lowest energy excited state. When you draw a simple picture of the S0, S1 and S2 state, in this picture you see that the S0 state is the so-called ground state, and S1 and S2 are the excited state. This is the first excited state. This is the second excited singlet state. When you give a high energy radiation, the molecule or the system comes to the S1 and S2 state both. But from the S2 state, you will notice that from the S2 state, there are two processes that happens. The first one is the radiative, and the second is the non-radiative relaxation. Since the energy gap is less, also this may be also one of the reason, the radiative non-radiative relaxation occurs very fast. In this non-radiative relaxation from S2 to S1, the emission occurs, and therefore it reaches to the S1 state immediately. Also, we had calculated that the total radiative time of this system, or this total transition, is a function of two, the rate constant of radiative and rate constant of non-radiative process. Since the rate constant of non-radiative process is quite high, the total radiative time reduces. Okay, and if the radiative time reduces, the fluorescence lifetime you get is still shorter than that. When the radiative or the fluorescence lifetime is still shorter, it is somewhere hidden in the whole steady state spectra, remains unnoticed. You cannot normally observe it in the steady state spectra, and is of very low intensity as well. So it is short lived. Okay, and if you remember, see here, say in this picture also we had discussed that there are two states in each. The first one is the S2 state and the second one is the dimeric S1 state. Immediately from the S2 state to S1 state, the relaxation happened to be in 0.2 picoseconds, and thus it is quite unobserved in the case of this tautomer. Okay, tautomeric emission. Now we'll go on to the next question, that is the question 8. And what does this question 8 say? The principal relaxation pathways in plasmonic nanoparticles are phonon-phonon coupling, electron-phonon coupling, and electron-electron scattering. Typical time scales of first, second, and third are respectively. Okay, so basically, this comes through this we switch to the next topic, that is the plasmonic nanoparticles. So, with the advancement in the nano range or the nanotechnology, we also came to know about the nanoparticles. Okay, and these plasmonic nanoparticles, what is this concept? So, for this, I have just added a picture to this. So, as you know, apart from the three states, we have two more states. Out of them, the one is the plasma state. Okay, so plasma. Okay, the writing is not very good. Wait. So there is one plasma state. Okay, and the particles in this state are called as the plasmons. Okay. So definition wise, what are plasmons? Plasmons are quanta of free electrons on the surface of metal. Okay. So, talking about the surface of metal, as you know, the nanoparticles, they have quite a high surface area, first of all. Okay, and thus, there are lot of free electrons on the surface. Uh, when you talk about these electrons, these are the conducting electrons, and therefore they together they form a quanta. And in order to get a simple explanation to whole concept, they consider that these quanta in the form of electron cloud, they oscillate along the particle, they oscillate around the particle. Okay, and since they are the charged ones, they also generate an electric field with the oscillation. Okay, so electric field with oscillation, right? Now, this gray one is called the metal surface. Now, suppose the electron cloud is in this side, the electric field is generated to that side, while the other way in this side. So, basically, this electric field is the oscillating one. So, here it is read as light induced collective oscillation of the conduction electrons at the surface of the metallic nanostructure. Uh, Basically, first of all, plasmons, these are the quanta of free electrons that are on the surface of matter, metal. Basic, and also if you talk about the nanoparticles, this plasmon peak is quite intense because of the reason that it has a high surface area, and there are loss there the intensity, therefore the intensity of the plasmon resonance you will get it quite high. Then we also discussed that this plasmon on the metal surface is in the form of electron cloud which oscillates along the surface. Then in this oscillation, it can move to and fro. When it moves to the direction, the electric field is generated in the opposite, and thus the direction of the electric field can be given in the form of the wave as it is shown in this picture. Okay, and what is this frequency? Now, what happens is basically absorption you get when absorption happens when the uh, oscillating frequency of plasmons resonates with the frequency of incident radiation, and that is how the absorption, wait a second, absorption happens, right? Now, this is the localized surface plasmon resonance. They have denoted it in the form of these spheres. After being excited, reaching to the excited state, what are the processes that can happen? So, the excited state relaxation processes can be as the first is the electron scattering. Okay, so the first process is after light irradiation and excitement of the electron to the other state, the scattering can happen. Okay, this process is of a low time scale of around 100 femtoseconds. Okay, so first process is the electron scattering. Then is the electron phonon coupling. What is this electron phonon coupling? Electron phonon coupling is the interaction of electron with the lattice vibrations. Okay, and this is a part of observed in crystals, right? Now the third is phonon coupling. What does this phonon coupling mean? To the it refers to the transfer of lattice vibrations from one lattice to another. Okay. So here the three things are the electron scattering, 100 seconds to 4 of femtoseconds. The second one is one electron phonon coupling, the interaction of this electron with the lattice vibrations, which is defined by the quanta of vibrations, that is the phonons, and the phonon that is the transfer of lattice vibrations. So the electron phonon coupling is ranges from 1 to 4 picoseconds, while the phonon coupling has a lifetime of 100 picoseconds. Here for the three processes or the three relaxation pathways that they had discussed, the phonon coupling has the largest time, that is the 100 picoseconds. So this is can be the option, this cannot be the option. Second is this second is the electron phonon coupling. So electron phonon coupling still has a higher time of, oh sorry, this one, 1 to 4 picoseconds, 1 to 4. So these two cannot be the right option because they have discussed about the respectively option. Then the third is the electron scattering, that is of 100 seconds of the femtoseconds. This is a very short lifetime process, and the answer to this question is this. Okay, so in this question, we just switch to a new topic, that is the plasmonic resonance. And the plasmonic resonance is something which is the characteristic of the nanoparticles, right? How the for the nanoparticles, the surface area is high with the most of the free electrons. The packet of this or the quanta of this free electrons on the surface of these nanoparticles or the metal is called as the plasmon. How does this plasmon get excited when because of the how is this considered? This plasmon is considered as that the free electron cloud. This free electron cloud oscillates along the metal surface. Say along the metal surface it oscillates in the positive and negative, or say to and fro directions. When this oscillates, it generates an electric field. This electric field, when the light is incident, the component or the electric field component of the light and the electric field component of this plasmon, when resonates, then this gives to the localized surface area plasmon resonance, which we discussed. As they excite and absorb the energy, they reach to a higher state. This higher state is represented in the second picture. That is, from the ground state, these electrons reach to the higher state. What are the processes that can be accompanied along with this change? The first one is the electron scattering that can occur from the excited state to the ground state. This is the first. The second is the electron phonon coupling. What is this electron phonon coupling? So the electron, when it interacts with the lattice vibration, say this one, then say this is a lattice, say a FCC centered lattice, then in this case the interaction of the two, this is called as the electron phonon coupling, while the third is the phonon coupling. Each of these relaxation pathways have a particular lifetime. Say as soon as the excitation happens, the electron scattering is of the least lifetime, that is of the 100 femtoseconds. The second one is of the electron phonon coupling, that still lies in the range of 1 to 4 picoseconds. The third one is the phonon coupling, which lies in the range of 100 picoseconds. Okay. Now, if you have any doubt in this plasmon thing and the nanoparticles thing, you can ask, or else we'll proceed to the next question. Okay, so now we'll go to the next question. that is read as electron phonon relaxation time of gold nanoparticle is similar as that of bulk gold when the pump power is. Okay. So, see, initially in this picture, we could also say that this frequency of oscillation also depends on three factors. The first one is the composition. The second one is geometry. The third one is the first one is composition, the second one is geometry of molecule, and the third one is, say, this is the chemical environment along it. Okay. So what is the third one? The third one is the chemical environment around it. Chemical environment refers to the molecules which are in around it. Yeah. So the electron phonon relaxation, which is time which is denoted by tau EPH, because it refers to the electron phonon relaxation time for the gold nanoparticle is similar to that of the bulk pump power. Okay. So what is the pump power? Actually, see, in each of these cases, the problem or the experiment that is conducted is the say the whole system is being excited using a pump beam or with a particular power. Then it reaches to an excited state. Immediately after delay of certain picoseconds of time, there is another probe wavelength of light. This is incident, and this is used to study the absorbance at each of the stages. When you study the absorbance, you get to know that at what point of time get the maximum absorbance and how it is decaying or so on, right? Now, for the case of gold nanoparticles, say what are the nanoparticles? Nanoparticles are, say, the small structures which are the aggregate of certain amount of, say, 50 to 100 number of the gold atoms. Okay, so these are absolutely minor structures that are in the range of nanometer, and that is why the fact they are called as the nanoparticles. Nowadays, after nanoparticles, there are nanorods, there are apart from nanorods, there can be nanotubes and many other nanostructures. And the distinct property of each these nanostructure is that the each nano sorry here nano particle differs in its property from that of bulk. Okay. Now see, this is the be, say this is the study of the delay time with respect to the pump power. So in each of these cases, the pump power is being changed. Okay, and with the increase in the pump power, you will notice that the value of the time constant for each one, say this one, or say this one, or this one, how it has changed. So as you can say, as the pump power is increased in the small picture, in this inset image, you will see as the pump power is increased from 0 to 1.2, there is increase in the relaxation time. Say this one is around zero point 0.8, then further it shows an increase to a maximum value. Okay, so the electron phonon relaxation time of the gold nanoparticle is similar to that of the bulk gold. Okay, now in order to check for that of the bulk gold, what they had taken, what they did, that was for the bulk gold and some where the pump power was zero, they had plotted this time, and for each case it came out to be 0.65 picosecond, which is same to that of the bulk. So for in this case, say they have taken that this is the time constant versus the diameter. Also, like with the change in the particle size, also they have noted the time constant and they have come to a conclusion that it is more or less the same. Got it? So, yeah, the electron phonon relaxation time, when calculated by changing the pump power which is used to excite the sample, then it was noticed that with the increase in the pump power, the relaxation time has increased. Why? Because as the pump power is increased, there are many other processes that come into existence. Because of this, the lifetime increases. Now, or the time constant increases, which we can observe from this diagram or from this picture. Also, they can say that this time constant, when they notice, or the effect of power, pump power, when they had to notice, they also took or they also recorded the relaxation time at zero pump power. And the value of the say what is the time constant for the zero pump power is equal to that of the uh, bulk gold. Okay, so the answer to this question is electron phonon relaxation time of gold nanoparticle is similar as that of bulk gold when the power or the pump power is zero. Okay. Now, if you have any doubt in this question, just ask, or else we'll go to the next question. In this graph, the only thing they have shown is as the diameter or as the size of these nanoparticles changes, irrespective of the diameter, the time constant remains the same, keeping the pump power constant. Okay. What we are changing, the factor that is changing is the size of the particle. It is becoming bigger from the say 3 nanometer to say 100 nanometer. Right? Now we'll go on to the question number 10 for this assignment. The question 10 states that with the increase in the size of the nanoparticles, the electron scattering time constant is. First of all, in each of these experiments, we'll notice that for each of the time constant for electron phonon coupling, we worked in the picoseconds range, that too of 0 to say 10. Then for the electron scattering, we have to work in femtoseconds. Okay. Yeah. So, what they did is in the yet another experiment which was done in this year 2000, they took silver nanoparticles and they had to calculate the electron scattering time constant with the change in size. You will notice here they have written the diameter for 1.6 nanometer, 3 nanometer, and 12 nanometer each. Okay, when they notice the with the probe delay for in the range of picoseconds, when they observed each for what they have shown that for each radius, say this 12 nanometer. Now in this particular experiment, what the thing that is changing is the particle size is constant. They have recorded it for the lifetime studies. How is it changing? Here in this case, they have increased the nanoparticle radius, and they have also related it with the tau, or the tau of electron scattering. And what they noticed is in this electron scattering, as they increase the particle size or say the radius. Okay, so for each of the cases, when they increase the nanoparticle size, it reaches to a maximum. with the radius increase. Okay. For each the radiative lifetime, it increases, as you can see, from 100 to 200 to 300 for each part radius they have seen. And as the radius changes, it reaches to a maximum. Okay. Now, here what are the options given to us? The first option, that is increases to saturation. Yeah. So this thing we have observed in this case. This is the say linear, not linearly, but and not monotonically also, from 0 to 14 nanometer of the diameter size, as this the value of this coupling is increasing to a maximum, so it increases and then it becomes almost constant, as is seen in the straight line, right? So it increases to saturation. The option it decreases to saturation is not correct, because here they are talking about the time constant, that is denoted by the tau. Okay. If they would have talked about the rate constant, then it would be the reverse. It would decrease with saturation because tau is inversely proportional to K. Then decreases or increases monotonically. So these two are also the wrong options. The correct option to this question is increases to saturation. Increases and reaches to max. Right? Now, uh, uh, whenever we study any graph, the thing which we should come, which the things which should come to our notice are, the first, what are the x and y axis, and second thing is what is the unit of those. The third is how can we create a relationship between by just following the graph. So in each of these observation also, earlier also, we had to also only notice how in each of the experiments that they had conducted with the silver or gold nanoparticle, how the things are changing. What are the factors which on which the value of this time constant depends. So first, as we had studied, this depends on composition, geometrical shape, and nature of chemical environment. So far, composition we have not studied, but we have studied how the shape or say the size matters. In this case, with the diameter, it remains constant, but with the pump power, it has sought to increase. Now, in the second case, say here in each case the time constant is increasing with the um, increase in the intensity of pump power. In the second case, for each electron coupling of the silver particles, uh, so the electron scattering time constant for the silver particles increases to reach a saturation value in case of silver, and it does not increase monotonically, it increases to saturation to reach a maximum. Okay. Okay, so now we'll go on to the next question, which is, in case of gold aggregates, the electron phonon relaxation time is independent of wavelength, decreases with increase. Similar to this, there is yet another experiment by this group, Link et al. In year 1999, where uh, they also observed it at different wavelength. Okay. And for each different wavelength, they had also observed that, say this is for the red one, that is a 535 nanometer to 560, or then 565, then 530 and 525. For each one, they have observed the intensity, and they just plotted it with the function of the time. So the for each time constant with the wavelength, they notice that it decreases. Say from 2, the time reaches to 0. Thus, with the increase in the wavelength, see here, with the increase in the wavelength, there is decrease in the time constant. So, what are the options given to us? Independent of wavelength, decreases with the increase in wavelength, increases with the increase in wavelength. first increases then decreases with the wavelength. So here in this spectra we observe a clear cut line, that is it is decreasing very finely with the increase in the wavelength. So the answer is quite clear from this observation that it decreases with increase in wavelength, although the case shown here is in this order. If we see, that is, yeah, in increase, if we see, yeah, if we see in this order, it is increases with decrease in wavelength, or say decrease with increase in wavelength, right? Okay. Now, with this, we'll go on to the next question. So far, if you have doubt in any of the questions, just ask. So here, what is it written? Increase in the electron oscillation phonon, spectral overlap, and interfacial scattering with the increasing extent of aggregation leading to the faster electron phonon relaxation time. Okay. So now we'll come to the question number 12. So far, what is the thing that they have discussed is, now suddenly we have jumped to a two component system of silver platinum, and these are the nanoparticles or the alloy particles of the gold and platinum, and in each of them they have given a equation. Okay, now what is the value of this tau? So there is a relation to calculate this tau. And what is this? How is this calculated? So this tau is a sum of is a sum of alpha au whole upon, yeah. So this relation is given by upon tau EPH of gold plus 1 minus alpha au of, this is for the platinum part and this is for the gold part. So this can be written as tau E minus pH of for platinum. Now for each of these components, to be more clear, what the final equation comes to be O. That is, so that is tau E pH due to both gold and platinum is alpha. Or now what is this alpha? So this is something similar to the mole fraction, but it is not equal to mole fraction. Okay. this, as we had studied in the Oswald's dilution, similar to that alpha also, this value is the real value and is lesser than the value or the value of x. So this is equal to tau EPH electron phonon for gold plus 1 minus alpha. Why is this alpha 1 minus alpha used? 1 minus alpha AU is used to denote for platinum because the total sum for each is comes to be 1. Then E minus pH of, say, platinum. Okay. Now just rearranging this equation, and that is not tau, that is 1 upon tau EPH. Now what we need to do is 1 upon tau EPH, or say EPH, is equals to alpha AU into tau EPH of AU, sorry, PT, right, plus 1 minus alpha AU. Okay, I'll write this on a fair page. Yeah, I can write it here. Say 1 upon tau EPH is equal to 1 upon tau EPH is equals to alpha AU whole upon, it is equal to tau EPH of gold plus alpha PT or platinum, sorry, not alpha, that we can write in terms of gold only, 1 minus alpha of AU or gold upon tau of, or the time of, wait for platinum, right? Now what we'll do is just take the LCM and we'll write tau EPH of AU into tau EPH of platinum, right? And here we'll bring these terms, alpha of AU into tau EPH of platinum plus 1 minus alpha AU into tau EPH of AU, right? Now the what we'll do is we'll take the reciprocal. This is equal to 1 upon tau E minus pH, right? Now we'll take the reciprocal. Taking the reciprocal, total time for each will be, say, tau EPH, not like this, EPH of AU multiplied by tau EPH of platinum whole upon alpha AU into tau EPH PT plus 1 minus alpha AU into tau EPH of AU, and bracket close. Now let us check what are the options given here. Finally, the expression that comes is, I'll just write it here, tau EPH of AU multiplied by tau EPH, that is of platinum, whole upon, say here in the bottom, it is alpha AU into tau EPH of PT plus 1 minus alpha AU into tau EPH of AU. Okay. Now based on all the options given here, the numerator term is almost constant in every case. This, this, and this tau EPH in of AU multiplied by lifetime, that is the time constant of platinum, upon this is the mole fraction of AU. So here it comes with multiplied with that of platinum and mole fraction of platinum multiplied by AU. So this is the right option in our question. Okay. Now also like see, we are talking about gold and platinum, right? And what the alpha is still a question. So how can we calculate alpha? So this alpha depends directly on the mole fraction of gold. As you increase the content of gold, you can say that yeah, alpha will increase. But all of this also depends on a factor, that is the rho, and this rho is called the density of state. So the density of the Fermi state. Fermi state, what is it? Fermi state is the highest energy filled state. So density of the Fermi level, right? So now from this whole, you see that, say if this is the absorbance of the pure AU for platinum and gold, it decreases. Okay, or say the decay decreases, or the decay decreases, and then here also, you will see there is a relation between the mole fraction of gold and the radiate this time, which you will notice that as the mole fraction of the gold increases, it reaches to a high value and reaches a max. Okay. Now, if you see closely here, this is 1. So, the 1 is equal to the pure gold. Okay, and not any alloy. And as you decrease the mole fraction, which means most of the platinum you are adding. Now here it shows that, see, if you decrease it to, say, if it is something 0.85 also, then you will notice as there is decrease in the mole fraction of gold from 1 to 0.85, there is a sharp decrease. And further, if you decrease it further, or further if you decrease the mole fraction of gold, there is not that much significant decrease as that is observed in the first case. So in the first case, that is a sharp decrease. In the further cases, there is quite less decrease, and all of this depends on the function, that is the density of the Fermi level of the gold. Okay. Now we'll also come to the next question, which is also similar to this formula. Okay, so in the next question, the variation in the electron phonon coupling of the gold and platinum alloy nanoparticles is not a linear composition because of the difference in the density states. This is the question which we have, or say this, from this equation we got to know that if the density of AU is equal to that of then density of PT, then in this case both the function will be equal to, say, 1, and what you will get at last is x plus 1 minus x. Both of these will be cancelled, and then alpha will be equal to the XAU. If you want me to just solve this question, let us consider a case where these two are equal. Okay, so let the density of epsilon F AU equal to the density of epsilon F PT. Of PT stands for platinum. Okay, now keeping this, I keep that x of sorry, x not alpha of AU. Okay, now I am considering these two to be equal, right? And therefore what I do is, here I can write, here also I've written that equation. So what I'll do is, in this part I will solve that question. Say, here I can write x of AU, and then I can write it as simply rho multiply by rho whole upon, say, since these two are equal, say this is also a, this is also a, what I can take common is this A, or this rho I have taken common, and in bracket it is x AU plus 1 minus x. These two get cancelled, and therefore it comes to be x into rho whole upon rho. And further these two get cancelled, and the value of alpha is equal to x. The condition where this thing is varied is only when the mole fraction of, sorry, the density of the states of the two is not equal. So this is the reason for the variation in the electron phonon coupling time, right? From that of the linear composition. Now, if it would be a linear composition, as the value of x increases, then the value of say tau would increase. Okay, or sorry, decrease. As the value of x decreases, or sorry, yeah, as the value of x decreases, yeah, increases, the value of tau would also increase and give a linear relation, right? Because in that case, all this would be 1 and alpha would be equal to x. And thus, for in this following equation, if the value of alpha becomes to be x, so everything is sorted. Now, so far in all these questions, if you have any doubt, just ask, or else we'll go on to like, since the time is also up, we'll discuss the rest of the question in next week session. If you have any doubt in any of these questions, please tell. Okay, so first of all, thank you so much for joining the session. With this, we conclude our week 10 session, and we'll meet in the next session. In each of these weeks, if you have any problem in any of the week questions, we can still discuss in the next week. Okay, so first of all, thank you so much.